Hey, how's it going? I'm Sage Hahn from the University of Vermont, and today this is going to be a relatively brief introduction to a toolbox I developed called the Brain Predictability Toolbox. This is the pre-recorded tutorial for the OHBM educational series. Let's just hop right in. So this talk today is about a Python-based library called Brain Predictability Toolbox, or we can just call it BPT because everyone loves acronyms. And it is a unified framework of machine learning tools. So what that means is it's basically just a Python library that will hopefully provide some useful functionality for doing some types of machine learning based neuroimaging analysis that are popular in the fields, working with sort of ROIs, which we'll do today in an example. Or if people are interested, there's also, I have a number of examples where working with sort of brain volumes or surfaces or more complex things. I was thinking we just dive straight into an example. We're going to be using this Aomic PIOP2 dataset, this small one here, which they have nicely made available. And we're going to be using Google Colab for this. Wasn't sure about the logistics, and I don't really love Google Colab, but basically, if people aren't familiar, it's like a free version of Jupyter Notebook, but it runs in your browser and it runs on like Google clusters somewhere. So hopefully I'll have some better way of sharing this link with everyone, because I don't think anyone wants to type this into their browser. 1BFGW8. Anyways, we can just hop right in. I'll leave this up. I guess if there's really no way to transfer it over, you could type that in. But assuming you get over there okay, and also assuming this is your first time using Google Colab, I forget exactly, but it might run you through, like you might just need to connect to your Google account. And if you don't have one, I apologize. Also, if you'd rather, I'll make some materials available, or like just this specific notebook available if you want to just follow along in a local notebook too, like in Jupyter Notebook or Jupyter Lab. I personally prefer that over Colab, but I think Colab is easier to share with other people. So that's what we'll be using today. And this will be a sort of self-contained example. So we'll download all the libraries and everything that we need within this Google Colab instance, and also the data we need. But I'll get to that more in a second. Basically, what we're going to be looking at is just, can we do something kind of simple? So our machine learning question of interest will be, can we use just cortical thickness ROIs from the standard free surfer distro parcellation? And can we predict the participant's age? And again, if we look here, there's about 226 subjects in this data set, and they collected a bunch of different modalities, but we'll basically only be using information in this example from these T1s and this age variable. All right, so hopping here, the first thing we're going to do is install the library. So the BPT library in this Python pip repository is called Brain Pred Toolbox, mostly because BPT was taken by some other library. And likewise with this other library, NeuroTools, which is called in pip BP-NeuroTools. And usually if you're installing this locally, you might run these pip commands sort of like from your terminal. But also within these interactive like IPython Google Colab notebooks, if you just add this exclamation point here, it's the same as running something from the command line. So like all of these commands here, you could translate locally just as something like that, like copying and pasting over. So yeah, these are the two main libraries we'll use, but they also each contain a number of dependencies. As you'll see, this output just streaming out. And there's one slightly annoying thing. You'll see we get this crazy error. And if you had just gone on and ran things, this will give you an error. Basically, there's a plotting library called matplotlib, and the pre-installed version, we don't need to get into the details. The practical matter is you have to go up here to runtime and click restart runtime. And we can see that shows up here. Or in the Jupyter notebook, if you're following along that way, they call them kernels, so it'll just be restart kernel. We don't need to download anything again. You'll see it just says you must restart the runtime in order to use the newly installed versions. Okay, so moving on from there, what we're going to do is download this basically pre-prepared quick start file, I call it, which is just, here we can run it. Again, we use this exclamation point. This wget just says download from somewhere on the internet. And this is purposely meant to be small. We follow this link here. We'll see just in this pre-prepared GitHub, I just went through and combined a few of these different files. So it's these like output free surfer stat files. And now it's just together in one CSV. You can open this to the side, participant ID, the thickness measurement, and then there should be age and sex all the way over at the end. Go back up here, we're still in intro and setup. This is kind of a nice part of Google Colab, even if I don't like the rest of it, is you can page around with these headers. So that installs the data we'll use. And the next thing we'll do is preparing our data into what PPT is called a dataset object. So if you're already somewhat familiar with Python, you'll see once we start using it that it looks pretty similar to the pandas data frame. That's because it is. It's basically just an extended version of the data frame. And the data frame, which is also, if you're coming from R, pretty similar to the data frame in R. But the basic idea is that we, down here, here's the actual code, here's the import, this is important. We first load the data from the CSV into this dataset data frame object, and we just give it a little bit of information. We say the index column is this column participant ID, and then by default we say we have these two targets or two potential targets. And then this command here just converts sex from like the string M's and F's to a binary variable, so just zeros and ones. So if we run this, we'll see it loads it in here. So one of the key differences between a data set and a data frame is this notion of like data and targets, so that area there. So the idea in BPT is that data is everything you load in is by default treated as data, which is basically just like any potential features or columns which might be used as input to a machine learning algorithm. And I call that a role. So another role are targets. So columns can be targets. And these would be variables which are potentially predicted by those other variables that are in the data. And then there's a third one, which I call non-input, but we're not going to use that in the example today. And we'll just treat these age and sex variables both as potential targets. And you can see that this just gives us a nice little output. And we can see the shape, 224 rows, and that looks good. So after you have your data loaded into a data set, there's sort of a next series of steps that you could do. Sort of these are like pre-machine learning steps. This will depend on the state of your data or whatever. Like if you're working with really raw data, there might be steps that you want to do before even loading it into BPT in the first place. But in this case, this data is pretty clean and well processed. They ran it through some pretty standardized pipelines at first, but one common technique, because neuroimaging data is usually noisy, so we can do something like filtering for outliers. So this step here, there's a built-in function. See, data equals data.filter outliers by standard deviation. And what this argument scope equals float means is just we want to apply this operation to any of these columns which aren't binary or categorical. So one way of looking at that is we can go in here and say data get calls float. And this will tell us all of the columns which fall under this scope, which is basically just a fancy way of indexing columns. And we'll go here and we'll see it's mostly just those ROIs. Essentially, we want to apply it to everything that isn't sex. So we can confirm, explicitly. It's not in it. So anyways, what this function does is it will go through column by column and it will look to see if any of the specific values are outside of, in this case, 10 standard deviations away from that column's mean. So we'll run this. Because the data is pretty clean, we'll see that we still have the same number of subjects. Nothing happened. But here I could show an example. So another thing is, if you don't do this assignment there, like if you just run this piece of the command, it will apply it to a copy of the data. So it won't actually do any changes. So let's apply a crazy filter. So drop any data points that are in any of the columns outside of one standard deviation. We go through and it drops everything. But you'll see that we just applied it to a copy. So all the data is still there. So this could be a way of testing it for like maybe 5 standard deviations. In this case, how many did it drop? We only dropped 1 in this case. But essentially this is just a technique for finding those really extreme outliers, where the pre-processing went crazy and it made 6 ROIs and there should be 150. As in the case of this distro atlas. So we'll skip this for now. There are other options too, like different encodings and things. You'll see before we just went from this sex variable to something else. These links here to the documentation. So you'll see there's a bunch of methods that you can potentially do for this data set, and they're broken up into a few different categories, like these encoding and data files and filtering and dropping and so on. For now though, again, our data is pretty much ready to go. We can see another example of something that might be useful in some cases. There's this function for printing information on some columns or data which might have missing data, but we don't have any missing data in this case, so it just prints nothing. Next, let's move on to some of the code. So again, here there's a section for plotting / viewing. So these are just tools to easily visualize some features. So for example, let's plot using, again, the scope argument. We're going to say let's plot both of the targets and then also just whatever this first random ROI is. So if we run this, we'll see we get just a quick age distribution, looks okay. This random left hemisphere frontomarginal gyrus and sulcus thickness distribution. It looks okay. The sex distribution, a little bit more females than males, but that should be okay. And then also there are some functions based on the Seaborn library if we want to do, for example, look at some bivariate relationships. So between this random ROI and age, and then also between sex and age. We can see there's some pretty easy ways to look at these variables. Just built into the package is just a general data science, not neuroimaging specific thing. It's usually a good idea to just go through and look at some simple, it's called exploratory data visualization. The idea is basically you want to catch these small errors that might sneak in. Maybe we go in here and we look at the age and the plot is instead goes out to 35,000 just because there's one random outlier. Someone's age added 2 zeros or something. That's the kind of thing you're looking for. Some other things you might look for are like highly skewed variables, which you might want to apply some transformation to. But in this case, these thickness ROIs are pretty uniform. So after this, we're going to dive just straight into the machine learning, everyone's favorite part. Although you can make a case that the beginning steps, these less glamorous steps, and a lot of the steps that weren't shown, these data cleaning and preparatory steps, are really the real meat of it. That's where if you do those steps right, the rest will sort of follow easily. But this is a machine learning library, so most of the focus of the tutorial will be on doing machine learning with this type of data. So in particular, most of the machine learning sort of workflow in BPT works through this evaluate method, which we're going to call here. And what we're going to use is our sort of machine learning pipeline. There are only a few sort of required parameters here and a bunch of optional ones, because we're going to use this pipeline called, it's just a reference to a default machine learning pipeline in the package called this ridge pipe. So what that means is it's going to be a ridge regression-based pipeline. We'll look a little later exactly what that is. And we're going to reference it, our prepared data set that we made here. And then we're just going to tell it to just use one job in this multiprocessing. And right away, you'll notice it started spitting out all this verbose output. And we're just mostly using just default parameters as much as possible. So we'll see the target it chose is age. That's kind of meaningful because we didn't tell it anything. So just it's using age because that was just the first target. But since we have 2 loaded, it'd actually be probably a better idea to run it explicitly with our target as age. We're using a regression problem type, that's right. We're using 148 features, which again is right because we loaded 150 in total, but 2 are these target features. So we're using all of those imaging features. Then you'll see there's this progress bar and then information across each of these 5 folds. So what these folds are is basically the predefined settings are to do basically CV equals 5. What that means is we're performing a 5-fold cross-validation across the whole data set. And it'll give us information sort of on each of these. And in this case too, it gives us, we put the results in this results object. So this is an instance of a class in Python of something called eval results. So if we go here, it basically keeps track of all this information. We'll just go through a few of these, but it also gives us this nice just output. So from this just very simple example using mostly defaults, we have an average across these 5 folds, an R squared of 10%, a negative mean squared error of minus 2.83. And then all of these different saved attributes of this object, and then some information on sort of the context that this object was evaluated in. So again, going back to this point a little earlier where we just said, let's use a ridge pipe as our predefined pipeline. So what do we even run? So one of the things we can look at here is this result.estimator, which stores the sort of lower level ski-learn, scikit-learn version of the estimator we run. And we'll see this is not exactly the most readable. There's some imputation steps, a scalar, one hot encoding, something called a search CV, and then a ridge, and then a lot of parameters. So this is basically an internal representation. What might be more helpful to look at is basically if we go into these default pipelines, we can see the BPT representation. So we'll see here the pipeline we ran is this series of steps which are applied in the context of cross-validation, basically as all of these steps one by one are fit on a training set that 4/5 of the data and then applied to the validation set, and that's repeated. We'll see we have 2 imputation steps, a scaling step, which just scales the data roughly to 0 mean and 1 standard deviation, a 1 hot encoding step, and then a ridge model where it has a parameter search over 60 parameters, 60 random parameters. So the idea here that you might notice is we have 2 imputation steps, but no missing data. We also have a 1 hot encoding step, but no categorical input data. So the idea here is in BPT, these pipelines are meant to be sort of reusable. So if there's no missing data, no harm done, these steps are just skipped. But we could use this exact same pipeline for a data set with missing data, or if it had categorical input variables, and it'll work sort of the same or add in or get rid of pieces as we go. Yeah, we can come back to that a little more in a bit. Another thing we might want to look at are the feature importances. So in this case, since we used a regularized ridge regression, the feature importances are these beta weights. And what we're saying here is, let's just look at the average of these beta weights over these 5 folds. If we didn't do that, it would look more like we could get them sort of raw, so the ones for each fold. But if we wanted to do some sort of visualization, maybe we want to look at the average over all 5. We go here. Now, let's say we want to plot them. For this, I'm going to show off this, I call it auto magical plotting function. So some mix of automatic and magical. And it's from this associated NeuroTools library. I might take a second to run. It has to reference some external data, but basically the idea is it will magically look at the names of these ROIs and these values, and it should just go in and make a plot of the data. And then what we're going to do in this next part of the example is, here it goes. So, not bad, not bad. And what we can also do is basically customize it. So this plotting function that we're using can be used to make a bunch of different plots. It has its own documentation. I have no idea where that, okay. With more options than you could likely ever want. So it's sort of a mixed bag. I'm going to We're in this next example, we're going to use FS average space, which is a higher resolution for plotting. We're also going to add a title and a specific threshold. I'm just going to stop for a second and let this run and come back when it's done, just since it takes about 3 minutes to run on Google Colab. And like magic, we are back, and the higher resolution plot has generated. And I've just gone ahead and started running some of the future cells too. So most of this tutorial isn't us just sitting staring at the screen. It's pretty slow, huh? Google Colab only has sort of limited resources, so it's a little slower. Things should be a little faster on your home computer, or definitely a cluster or something like that if you have access. So here's a brain plot. Maybe it's meaningful for some of you. Look at these age-related beta weights. Anyways, the next thing we're going to move on to, just jumping around to some of the functionality of the library, are running a permutation test. So especially when our sort of cross-validation validation strategy of choice is something like 5-fold cross-validation, if you want to get any idea of the sort of significance of the results or if they're meaningful, one of the ways is to use the permutation test, where you essentially just, in the simplest case, just permute the target labels, so the age between participants, and you treat that as your null model. So in this case, again, because Google Colab is slow, we're only doing 10 permutations, so that limits our potential p-value, because it's basically where does it fit into this null permutation or null distribution we generate. You can see our real results are way out here at 10% of the variance, or out here, and the null model is pretty nicely centered around 0 or maybe a little below 0. Yeah, and we can see these p-values. This is the lowest we can possibly get with 10 permutations. But it runs straight from this results object. The idea is this is just a nice potential way of sort of increasing the robustness of your results just straight away from what's already there. And another interesting thing which is built in is sort of this powerful extension to the permutation test, where we're passing this extra argument that says blocks. So what this is saying is now we're performing constrained permutations, where in the first model we didn't pass anything, so any two subjects or participants, ages could be swapped. But if we pass a block argument with sex, now what we're saying is the only valid swaps which are allowed are people of the same sex. So now our null model, these results in blue here, are explicitly showing they would still have built into them any sex effects. So if, for example, our results were just secretly being driven just by sex, permuting the labels within sex would give us the same result as our true results. So where this can be really useful is in multi-site data, and if you pass blocks as the site variable. So the idea is some scanner effects can leak in, but if you explicitly make sure your null model is sort of accounting for that, it's and your site's sort of balanced in some way or whatever, it can be a good way of testing to see if your results are being driven by site or not. So you may be wondering about different machine learning models, or do we have to just use this ridge pipe, or is it recommended to just use this ridge pipe? And I think this is a kind of interesting topic in general, because it's, in some ways, it's a good idea to try different machine learning pipelines like elastic net or gradient boosting or support vector machines. But in another way, it can sort of quickly become this basically just like researcher degree of freedom. And if you don't do things right, again, I'll try try and explain what that means. It can sort of, you get into this shady realm of almost like p hacking, or in areas where you maybe don't necessarily mean to, but you try one model and then you try another model, and then maybe you tweak the model that's working the best, and then when you're reporting the results, you're a little bit forgetful with which ones you actually report. So sort of to outline this, I'm going to be using this special compare object from BPT, and we're going to be looking over 3 sort of default pipelines. And what this will do, we can see here, is it will just, we can pass this now as our pipeline to the evaluate function, and it will run this comparison, which should finish in a second. But the point I'm trying to highlight here is essentially, this is okay to do. But one thing to note is we're testing all 3 of these with our full 5-fold cross-validation. So the idea is this is fine as long as these are results we care about. As long as sort of, I guess, part of the reporting that we eventually do is to say, this is an interesting comparison. The ridge pipe performed this well, the elastic net-based pipeline performed this well, and the gradient boosting pipeline performed this well, however well. Okay, and back to when it's actually done running. What I was saying was, essentially, if you run this type of comparison, you're testing everything on everything, you get all of these results. The, I guess, dishonest version would be to just go in and say, oh, which pipeline works the best, just report those results, and sort of selectively forget that you ever tried other things. Which isn't to say you never want to try different pipelines, but basically you need to be careful with how you do it in terms of cross-validation. So as an example of how you might do it more properly, the idea is you want to use nested cross-validation. So in the same way that in this bridge pipeline we've already been using, these hyperparameters have been set through nested cross-validation. So in this case, we'll just do a quick example of a train test split. So it's a global train test split. And again, I want to make this clear, but this next part of the example would be under the assumption that, one, we didn't really care which machine learning pipeline we ended up with. That also, we did this instead of what we already ran below. So this is just the code for, we're going to do this on a copy of the data set, and then we just apply a test split. We can see 180 subjects is our training set, 45 subjects is our left-to-side test split. There's just some coloring to show which subjects are which in this visual representation. But then we would run the exact same thing as before. So pass these compare pipes, pass our new train test set, use just our training subjects in this evaluate loop. This part's different. So basically now we're doing this 5-fold cross-validation across these 3 pipelines, except just on our training set of subjects. Now, if we look at this results summary, we don't necessarily need to report these results. We could, but because we still have this left-to-side 45 subjects, what we can now do is use these sort of intermediate results on just our training set and use this information, say, oh, the ridge pipeline does the best. And we evaluate just the ridge pipeline on the full data set. So it isn't said here, but we could just as easily say subjects equal all. That's sort of implicit. And use this CV test. So what that's saying is use the whole entire training set, 179 participants, and then use the whole testing set as our validation set. And this would be a way of still performing pipeline selection, but without violating that sort of double dipping. And sort of one of the reasons that is something we need to worry about is because sort of there's there's just a lot of error, especially when we only have, I don't know, 200 subjects. What we're doing next in this little example is we're using as our cross-validation sort of repeated train test splits. And we're going to do that 20 times with just the ridge pipe. And then we're just making a distribution of all the results. And the whole point of this here is just to say, look at this sort of incredible variability in what we get. So like up here, this result here, we train on all our subjects and test on a test set. If we did that 20 times with 20 different splits, we get this huge range. Some even don't predict at all. Some go up to about 15% R squared. The point is basically, one, you probably want more subjects than we're using in this example. And two, it's because cross-validation, because it's so easy to sort of work your results like this, you need to be really careful with the steps that you do. And again, I just have another example to make this really clear, like something you definitely don't want to do. Like you could, for example, change the random state and let's say do a 3-fold cross-validation on the full data set, using the full data set again. And just by changing the random state, get this huge range of different scores. So the extremely dishonest thing to do in this case would be you just change the random state a bunch of times, see the one that does the best, random state 0, and you run just random state 0, and you pretend that those were your results the whole time. Now, again, that's sort of just like clear-cut dishonesty, but and also sort of cheating, but it can be easy to accidentally sort of end up doing something similar to even just this obvious example of trying a bunch of things, seeing what works the best, and just reporting what works the best. So like an easy solution here instead would be, don't report just this 14% R squared, report the average over all of these. Or same thing with this one above. Instead of doing just one trained test split, because we know there's all this variability, we could just report instead over the average of all 20 instead. Again, cross-validation is kind of complicated, and it's pretty easy to make mistakes. Feel free to read through these examples a little more closely. I do have some longer text trying to explain things. But some of it you just have to get a feel for, mostly by messing up, getting results that look too good to be true, and then just stopping and thinking about maybe what went wrong. So for the last little bit of this example, we'll shift gears a little bit. I'll just show sort of the versatility of the library, or the attempted versatility, where let's use the same ridge pipeline from before, but now we're going to change our target. And now we're in a binary problem, predicting sex, binary. We can see the same ridge pipe from before, it works fine. And now we have some different default metrics. So the idea would be you can use a lot of these objects for regression, binary, multi-class, doesn't matter. We'll see if we look at this explicit estimator, the actual object itself, not that anyone actually read all that before, but now it's a logistic regression instead of before it was a linear regression, and some of the parameters have changed. And sort of more advanced users might be more interested. We could see in our sort of object itself, this ridge pipe, we're just saying params equals 1. So what the hell does that mean? Basically, it just refers to, in this preset 1, there's different arguments, different preset parameters that you can reference by these. So we were just referencing a preset 1. But you could also specify sort of, this is where we look at this parameter. You could also specify a custom one, for example. So we could say, instead of whatever this default 1 was, which explicitly is, if we go here to ridge, this 1 is basically just the strength of regularization from a really small number to 1,000. In this case, what if we just did it between 1 and 100, didn't optimize anything else? We can see we replace the 1 with this, we can rerun everything again, and we get different results, which I think are a little worse than before. And referring briefly back to our topic of cheating with cross-validation things, I think in general, especially if you're a little bit newer, this is another area where you probably want to avoid just making arbitrary tweaks unless you know what you're doing, because then you maybe end up in an area with, oh, what if I rerun this with 1,000? What about 1,001, 1,002, 1,003? And then eventually you just get results which are sort of by chance ended up good. Hopefully that's clear. Then the last thing I'll just show, again, is more of a little more advanced user tidbit, is you can also, if you're familiar with sklearn, you could pass in these objects directly. So you could, they have a built-in logistic regression with cross-validation also with some preset stuff, so we could just pass in that directly and run it and get results. Yeah, that's about it for this example. Thanks, sorry about this sort of chaotic nature of it. Hopefully this was helpful. I just want to point people to a few different things. There's this user guide here with some different outlining things, and then a bunch of different more full, more real world example problems. There's also this larger sort of method series, which this is a part of. This specific notebook is a part of, which uses those Aomic data sets and is going to be performing like a bunch of different analysis, maybe some DTI, fMRI, and free surface stuff. Also, there's the BPT GitHub, which I'd recommend people go to, and you can create issues or whatever if you have any questions or anything like that. Thanks so much.